Welcome to the riverbank. Here, the water's surface is 0. Above the line, herons stand on the sandy bank in positive territory. Below the line, otters dive into negative depths. Ripples spread out from 0 to mark the integers. These fixed tick marks help us navigate the landscape. But the integers only mark certain spots. Between those ripples are empty, glowing gaps, unclassified spaces we must identify to complete our riverbank map. To place a specific point in those gaps, we translate its value into a decimal expansion. This decimal behavior is the key to distinguishing between rational and irrational numbers. A rational number is defined as a ratio of integers. Its decimal form must do one of two things. It either comes to a definitive end, or it settles into a block that repeats forever. Take the decimal 0.2727. Because the digits 2 and 7 repeat in a fixed block, it meets the requirement for a rational number. Compare that to 0.101000. The jumping arcs show that while there is a predictable pattern of growing zeros, there is no fixed block of digits repeating here. A predictable pattern is not the same as a repeating decimal. If the length of the segments between the ones is constantly changing, the decimal is not repeating. 0.27 repeating is rational because of that repeating block. The expanding 0 decimal is irrational because it never terminates and never repeats a fixed sequence. This lack of a terminating end or a repeating block is what defines an irrational number. Look closely at the space between the ripples for 1 and 2. A heron stands over a specific point, the square root of 2. Because 2 is not a perfect square, its square root cannot be written as a ratio of integers. It expands into a string of digits that shows no sign of stopping. Based on the fact that 2 is a non-perfect square, what should we expect from its decimal form? Will it terminate, repeat, or do neither? It does neither. Since 2 is not a perfect square, the decimal expansion for its square root continues indefinitely without ever settling into a repeating pattern. Identifying a non-perfect square allows you to immediately classify it as an irrational entity that can't be expressed as a simple fraction. Consider a student who argues that 7/8 is not a rational number because it isn't an integer. We can find the correction by looking at the gap between 0 and 1. The definition of rational only requires that the number can be written as a ratio of integers. 7/8 already fits that description perfectly. When we convert that fraction to its decimal form, 0.875, we see it come to a definitive end. 7/8 is rational because it is a ratio of integers and its decimal form terminates. Rational numbers behave like the heron's steps, orderly and predictable. Irrational numbers are like the flowing water on the right, continuing without a repeating block or a final stop. To classify any point on the bank, use the formula. This is rational or irrational because of its decimal behavior. As you work, remember the mantra, watch the direction and the size. Distinguishing these numbers allows us to account for every point on the line. This builds the skills you need to work with the radicals and complex number systems you'll encounter in high school.